Section 1.3, well, we have few definitions to go by and properties to know. This is just us getting to know the language. Talks about matrices and matrix operations. We start with what a matrix is. A matrix is a rectangular array of numbers. The numbers in the array are called entries of the matrix. So, we're familiar with that. You put numbers, and then you determine directions. Now, diagonal of a matrix. If they want to talk about a matrix, let's make it here. Let's say A, B, C, D, E, F, G, H, I. So that's a matrix. That's an array of numbers. Diagonal of a matrix of an m by n would be A sub ij, where I equal j. That would be like, in reality, A sub 1, 1, 2, 2, 3. You know what? I messed up big time. Let me do it again. Start over. A11, A12, A13, A21, A22, A23, A31, A32, and A33. The diagonal matrix will be where the entries I and j are equal. Basically, you come just straight across the diagonal like you would a rectangle. Now, m by n is really the dimensions of a matrix. And that pretty much talks about rows first, columns after. So you always start this way. That's the first number. And then you start this way, and that's the second number. And you say that's a dimension of the matrix. An m by n matrix whose entries are all zeros is called the zero matrix. And we write it normally as just zero. Identity is like a 1. Is the matrix that has 1 across all of its diagonals and 0 everywhere else. So across the diagonal you see 1s, and anywhere else you see zeros. That's called the identity. That's what you multiply any matrix with and you get it back. To add or subtract matrices, they must have the same dimensions. To add them, they must match. And when you add the matrices, you simply add or subtract the corresponding entries, so you match, the first with the first, the second with the second, the third with the third, and the fourth. Again, I'm going to go over an example on each of those. If k is a constant or a scalar, in vector language we call it scalar, then when you multiply a matrix by a number, you simply multiply each entry by that number. Two matrices are equal if and only if the corresponding entries are equal. They have to be identical. Now, this is something that comes up in a lot of theorems we're going to get used to. AB, we could think of B as so we call this vector B1, we call this vector B2, all the way to vector Bn. And when you multiply those, you simply multiply A by each. Or you could go the other way around. You could say, you know what? No. A. You know how A is? You could call A that A1, that A2, and multiply it by B. And it turns out multiplying each one of those by B. Now we're going to do this in a much different way, but the definitions and theorems mention those, and I'll elaborate on that as we go on. Partitioning, we don't do that a lot, but you could partition a matrix. So a matrix can be subdivided into smaller matrices by inserting horizontal and vertical rules between selected rows and columns. For example, you could call this A11, A12, A21, and A22 if you wish. Or You could say, you know what, forget that, I want to cut it into 3 rows. Well, that's row 1, that's row 2, that's row 3. Or you could say, I want it to be column 1, column 2, column 3, and column 4. And that's how you could write it. Now we need to talk about a transpose. What a transpose does, it switches the rows with the columns. It makes that and put it as a row, and it takes that and make it as a row. Another way of looking at it, you maintain the diagonal and you just switch across the diagonal. But what it does, it switches here. It's not going to matter because this is, so let me make it even more interesting. Again, we're going to elaborate on everything I'm giving you. I know there's a lot of definitions there, but I need to really, I can't seem to find an example that has each of those individually. This is a 3 by 2. It has 1, 2, 3 rows, 2 columns. If I want to take the transpose, transpose of that, if this is matrix A, if I want A transpose, that will switch. That will make that A, C, E, and that will make this B, D, F, and that will be 2 by 3. But if it is a square matrix is when the rows and the columns are equal, then the diagonal method I just showed you works. Let's look at some examples and apply all of this. And again, it's just the language we're going to use all throughout. Suppose A, B, C, D, E, and whenever we're talking about a matrix, we use capital letter. So A is a 4 by 5, 4 rows, 5 columns, 4 by 5, 5 by 2, 4 by 2, and 5 by 4. Now, let me check on something really quick. And yep, I knew I left something out. Let me get that out of the way. Matrix multiplication. If you want to take a matrix A, m by n, and matrix B is an n by l, if you want to multiply them, the inners must match. And the outcome is a matrix with the following dimensions. So multiplying matrices is very tricky. And be careful, AB and BA are not the same. I'm going to elaborate on that with the first example and go from there. We're going to spend time talking about how to multiply matrices and see how this works. So in the book, they talk about multiplying matrices like this or like this. I'll show you that, what they mean by that, but I'll show you a better way of doing this. But for now, you need to know that whenever you multiply matrices, the inners must match. So when they say, hey, in each part, determine whether the given matrix expression is defined. For those that are defined, give the size of the resulting matrix. Well, what's C? C is a 5 by 2. Now, if D is 4 by 2, D transpose is they interchange the rows with the column. As you see, this was 3 by 2, it became 2 by 3. Since this is 4 by 2, it's going to become 2 by 4. And since the inners match, that is possible, and the outcome is a matrix, call it A, that is a 5 by 4. So they're asking, in each part, determine whether the given matrix expression is defined. It is defined. And for those that are defined, give the size of the resulting matrix. It's 5 by 4. Let's do B. Is that possible? And if this possible, tell me what that's going to be. And what do we think? If I take D, D is 4 by 2. And C, C is 5 by 2. Since the inners don't match, this is not defined, which means you can't multiply such matrices. BC, well, let's see what BC is. B is 4 by 5. C is 5 by 2. The outcome, call that matrix F, and that is, I shouldn't have called it A because there's an A there. I'm going to call this F as well, because they have reserved A, B, C, D, and E. All right. So here, the inners match. Matrix F, which is the result, will be a 4 by 2. Now, multiplying a matrix by a number doesn't change its dimension. What's D? D is 4 by 2. If I'm adding or subtracting, they must match, and the outcome will be matrix G, and that will be a 4 by 2. How about here? Well, order of operations. Let's see if this is possible. B is 4 by 5. E is 5 by 4. The multiplication is possible, and the outcome is 4 by 4. Let's say G. I'm going to multiply it by the transpose of D. Well, if D is 2 by 4, 4 by 2, then D transpose is 2 by 4. The inners match, and the outcome is a 2 by 4 matrix. How about here? B transpose. B transpose is, if this is 5 by 4, I'm sorry, is this 4 by 5? This is 5 by 4. And D happened to be 4 by 2. So this is possible. And the outcome is a matrix G that is 5 by 2. ED, I'm adding. E happens to be 5 by 4, and D happen to be 4 by 2. So that matches. I'll get another matrix, let's say GH, matrix H, which is a 5 by 2. And if I'm adding, they have to be exactly the same, and that's possible, and the outcome is 5 by 2. Now let's get our hands dirty and do a few of those. So here we are. Matrix A is 1, 2, 3 by 2. B is a square matrix. That means the number of columns equal the number of rows. C is 1, 2 by 1, 2, 3. This is a square matrix, and this is a square matrix. The number of rows equal the number of columns. When they say, use the following matrix to compute the indicated expressions, if it's defined, well, okay. 2A transpose. 2A transpose will be what? If A transpose is 3 by, if A is 3 by 2, this is going to be 2 by 3. You're going to take this column and make it a row, and you're going to take this column and make it the second row. All right, very good. And if I multiply by 2, that's simply 6. Wait, I'm missing something. That is 3, negative 1, 1. If you multiply by 2, that becomes 6, negative 2, 2, 0, 4, 2. And I'm going to add that to C. C happened to be a 1, 4, 2, 3, 1, 5. Need more space. Let's get more space. So this is 2 by 3. This is 2 by 3. If I'm adding or subtracting, the dimensions must match, and they do. And that turns out to be 6 plus 1, which is 7, negative 2 plus, which is a 2, 2 plus 2, which is a 4, 0 plus 3. Again, you add the associated entries. It's fairly simple. And there it is. We're done. All right. Now, D transpose. D is right there, 3 by 3. That transpose is 3 by 3 as well. If it's a square matrix, kind of like You press the diagonal, switch those. So that's a -1, that's a 5. Switch those, that becomes a 3, that becomes a 2, and switch those, that becomes a 1, that becomes a 2. Or forget all of that switching business. Make that the first row, there it is. Make that the second row, there it is. And make that the third row, there it is. So however, whatever works. I want to take this and subtract it from E transpose. E transpose is also 3 by 3. Take this, make it 6, -1, 4. 1, 1, 1 becomes the next row, and 3, 2, 3. And you just subtract those accordingly. 1 minus 6 is -5. -1 minus 1 is 0. 3 minus 4 is -1. 5 minus 1 is 4. 0 minus 1 is -1. And 2 minus 1 is 1. 2 minus 3 is -1. 1 minus 2 is -1. And 4 minus 3 is 1. If I make a mistake in the computation, you just need to understand the concept, and hopefully you are. And how about this problem? Well, what do they want us? Order of operations. Do the inside of the parentheses first. Can you take D? What's D? D is 1, 5, 2, -1, 0, 1, 3, 2, 4. And subtract it from E, which is 6, 1, 3, -1, 2, and 4, 1, 3. And what would that be? That will be a 3 by 3. Did I just do that? No, I didn't. 1 minus 6 is -5. 1 minus 1 is 0, and 1 minus 3 is a -2. -1 plus 1 is 0. 0 minus 1 is -1, and 1 minus 2 is -1. 3 minus 4 is -1. 2 minus 1 is 1, and 4 minus 3 is 1. Then I need to take the transpose of that. And what does that become? Switch the rows with the columns, and everybody's happy. This is the first column. It becomes -5, 0, -1. Second column becomes the row, and the third. And there's my answer. So again, a lot of really small details, but the good news is we're going to work with that for a while. Here's the definition. If you want to find the trace, it says a matrix, it has to be a square matrix. Then the trace is defined to be the sum of the entries of the diagonals. So if I have A, B, C, D, E, F, G, H, I, if I want to take the trace of this matrix A, that's simply A plus E plus I. The sum of its diagonals, nothing more. Really simple. So I want to find the trace of DE. Let me figure out what that is. Well, DE, what's D? D was let me copy that. And I just copied those. Here we're going to learn how to multiply according to the theorem. If you want to find D E transpose, well, D is pretty much 1, 5, 2, -1, 0, 1, 3, 2, 4. Multiply by the transpose of this. So this column becomes the row. Remember multiplication, this is 3 by 3, this is 3 by 3, the inners match. So the outcome is a 3 by 3, that's easy. Well, let's see. This is really how we figure this out. I'll show you how they do it in the book as well. The way it works, I always go in order. To figure out the first row, I use the first row. If I want to figure out what this is, I'll match it with the second. And the way it works, you multiply the first entry times the first entry, that's -1, plus 5 plus 4. So you multiply accordingly. That's why the inners have to match. Let me expand this a bit. Let me expand it long enough. So again, to generate the first, I need the first. If I wanted this specific entry, I'm going to have to use that column. So 1 times -1 is -1. Plus 5 times 1 is 5. Plus 2 times 2 is 4. If I wanted to find this entry, then I'm going to have to use row 3. And to find the first entry, I have to use the first. So the first will get me those 3. If I want to find that entry, I just have to match this, this with this. And I multiply 3 times 6 is 18. Plus 2 times 1 is 2. Plus 4 times 3 is 12. So let me find the first whole row. To find the first row, I have to use this. To get the first, I use the first. 1 times 6, that's 6, plus 5 times 1 is 5, and 2 times 3 is 6. To get the third, I use the third. 1 times 4, plus 5 times 1 is 5, plus 3 times 2 is 6. Now to generate the second entry, the second row, I use the second row. And similarly, to get the first, I use the first, second, and third. -1 times 6 is -6. 0 times 1 is 0. And 1 times 3 is 3. To get the second, I use the second. Again, it's always going to be that. -1 times -1 is 1, plus 0 plus 2. And to get the third, I use the third, using always that. -1 times 4 is -4, plus 0 plus 3. Now to get the green, I have to use this. Get that second, I use the second. I know I'm cluttering this. -3 plus 2 plus 8. And to get the last, I use the last. 12 plus 2 plus 12. And again, a lot of computation. This turns out to be 6, 12, 17, 3, -3, -6 plus 3, 18. The last one was what? It was 18 plus 2 plus 12, 32. Then we have 5, 9, 8. Then we have 10, 15. And then we have 3 and -1. And we are holding -3 plus 2, 10, 7. And we're having a 12 plus 2 plus 12, 24, 26. But we want to take, I did the transpose, right? Oh yeah, I did. So this is DE. If you want to take the transpose of that, I'm sorry, if you want to take, oh boy, okay, you know what it is. There's the transpose. We already did this. If you want the trace of that, you simply add those 3. You will say that's 17 plus 3 plus 26. What is that? 20, 46. So multiplication is a lot of work, but we're going to multiply matrices a lot. And keep in mind, DE transpose is not the same as D transpose E. If I want to find the trace of BC, first I have to figure out what BC is. I put those in order, see if I could multiply them. 2 by 2. 2 by 3. The inners match, and the outcome is 2 by 3. There you go. To generate this first row, I must use the first row. That's always how I see it. That's how I was taught. To generate the first entry, use the first, and again you go in order. 0 times 1, that's 0 plus 4, and that's why you check that the inners match. You're never gonna run out. To get the second, I use the second. 0 times 4 is 0 minus 4, and to get the third, I use the third. 0 times 2, that's 0 minus 20. To get the second row, I must use the second row, and the same idea. Use the first for the first. So 0 plus 6, and 0 plus 2, and 0 plus 10. I'm going to shrink that a bit. And we want to figure out what this is. And that turns out to be negative 12, negative 4, negative 20. And 6, 2, and a 10. AB. Now, if I want to find the trace of that, we have a problem. This is not a square matrix, it's undefined. To find this trace of a matrix, it has to be a square matrix. If A is a square matrix, then the trace of A denoted by is the sum of the entries. The trace of A is undefined if A is not a square matrix. You can't do that. Same thing with inverse, same thing with identity. All right, here's a definition. Linear combination, a topic that's going to follow us. We're not going to go in details, full details about it now because it doesn't apply fully right now. If A1, A2, all the way through A sub n are matrices of the same size, and C1, C2 all the way are scalars, constants, then the expression, if you take a combination multiplying C1 times A1 plus C2 times A2, we say this is called a linear combination of A1 through A sub n up sub r with coefficients C1 through C sub r. It says use matrices A and B from exercise 7 and 8. Let me get those. Okay, I did get them. Express each column of vector AB, the product AB, as a linear combination of the columns of A. The columns of A are well, let's see how I'm going to do this. Let me copy this a few times. So you take the columns. It says express each column vectors of AB as a linear combination of A. You list the columns of A and you start 6 plus 0 plus 7, whatever that is. And then for the second, use the second. Negative 2 plus a 1 plus 7. And that's going to give you a 3 by 3. That's the answer that you're looking for. And then, oh wait, I was trying to save time. I need to shrink this and move it a bit. Here we go. And then for the third, we would take the third vector. That will be 4 plus 3 times plus 5 times. And again, in case you're wondering, that would become what? 18 plus 0 plus 49. What's 18 plus 49? So that is 67. This will become a 36 plus 0, 36 and 28, 54. And 0 plus 0 plus 63. There you go. And you do the same here, and you do the same here. And this vector right here will be a linear combination of those three vectors. And that's how the idea works. Of course, you could go the other way around. You could say express the product BA as a linear combination of the columns of B. And again, we could see in B we have 6, 0, 7. We have negative 2, 1, 7. And we have 4, 3, 5. Linear combination will be take a 3 plus a 6 plus a 0. Whatever that is. And of course, there are 3 of those you could do, right? You could copy the blue again -2 times 5 times 4, and you could copy the blue again, the 3 vectors, 7 times plus 4 plus 9, where you see those, and whatever that gives you. For example, this is 18 minus 12 plus 0, that's 6. This is 0 plus 6 plus 0, which is 6. 21 plus 42 plus 0, 21 plus 42, 363. So this is a linear combination of those 3 vectors. And that's how the idea works. Now, I didn't really put this in a definition because it doesn't really need a definition. Given matrix, this find matrix A, X, and B to write this expression as AX equal B. It's simple. The matrix will be the coefficients 1, -2, 3, 2, 1, 0, 0, -3, 4, and 1, 0, 1. Now, this vector pretty much resembles those in order. x1, x2, x3. So basically, there's A, there's a vector B, and a vector x, and a vector B would simply be the constants. So this is really fairly simple to do, which is why I didn't go by the definition and burn you with that. Same deal here. If I really wanted to write this, this is 3, -1, 0, 3, 5, make sure those are lined up, and 2, 3, -2, 1. That's matrix A. Now the vector x will resemble the variables. What are they? If it's x, y, and z, you write x, y, and z. In this case, it's x1, x2, x3. And let me elaborate on what that means. Notice what you're doing. You're taking a matrix and writing it as a matrix equation. Notice this is 3 by 3. This is 3 by 1. If I multiply, the outcome is 3 by 1. If you want to multiply, don't you take this to generate the first, multiply it by this? Well, that's 3x1 plus 3x2 plus 3x3 equal a -3, and you can get it back. And the next list wants you to go the other way around. Well, no problem. There it is. This is 3 by 3. This is 3 by 1. The outcome is 3 by 1. And when you set it equal to that, you're going to set the first entry equal to 2, the second entry equal -1, and the third entry equal to 4. What's the first entry? Well, it's going to be this times this. That is 3x1 minus x2 plus 2x3. This is really not that bad at all. You could see it hopefully clearly. -2x1 plus x2 plus 5x3. Here again, same deal. We would say this is 3w minus 2x plus z equal 0, and 5w, there's no x, plus 2y minus 2z equal 0, 3w plus x plus 4y plus 7z equal 0, and -2w. We normally write x first, but you know, whatever they write. And there it is. And the last couple of problems are really pretty much making sure you know how to multiply and set accordingly. Let's see if we could do this. You could do this in any order you want. Now, I don't have any specific order to do this. This is 3 by 1. This is 3 by 3. This is 3 by 1. The outcome is 3 by 1. This is 1 by 3. If you multiply, the outcome is 1 by 3. So let's go from left to right. If I take those two first, and again, it doesn't matter how you do this. Let's do this. The inners are 3 by 3. The outcome is 1 by 3. And how does it work? Well, to generate this row, I need this row. To get the first entry, I use the first. So that's 2 plus 4 plus 0. 2 plus 4 plus 0. To get the second entry, use the second entry. 2 plus 0 plus 3k. And 2 plus 0 plus 6 plus k. So the first two gave me 6, 2 plus 3k, and 6 plus k. Now I'm going to multiply that by 2k. This is 1 by 3. This is 3 by 1. The outcome is 1 by 1. And what is that? That is 12 plus 4 plus 6k plus 6k plus k squared. And that equals a 0. So that is k squared plus 12k plus 16 equal a 0. That is k plus, let's see how that works. To get a 12 out of those, if I go by, let me check. Yeah, I figured I made a mistake here. 2 times 2 is a 4. So when I multiply that, that gives me an 8. That makes this a 20. And that's really k plus, to get a 12, k plus 10 into k plus 2 equal a 0, and k would be a negative 10. And again, they give you something basic. They just want to make sure that you are following the multiplication. And again, you could multiply in any order you want. It doesn't matter. And here we have the same deal. Let's see how this works. It says, use the column row expansion of A, B to express their product as a sum of matrix products. Okay, let's see what that means. Well, if you can ignore the directions on this one and just find AB for me. Again, for practice, I need matrix multiplication is a must. The inners match, the outcome is a 3 by 3. Now, I'm going to mention what they're talking about, but again, that's not something that we need for now. I just want to make sure we can get this going. Oh, the mess. Oh, come on. The outcome is 2 by 3. There you go. To generate the first, use the first. Well, multiply it by this. 0 plus 6, 0 plus 0, and 0 minus 4. To generate the second row, use the second row, and you multiply accordingly. That is 4 plus 9 is 13. 16 plus 0 is 16, and 4 minus 6 is negative 2. There. So what they really could do, they could write this as 0, 4 times 1, 4, 1 plus negative 2, 3, negative 2, negative 3 times negative 3, 0, 2. Notice this is 2 by 1. This is a 1 by 3. The outcome is 2 by 3. This is a 2 by 1. This is 1 by 3. The outcome is 2 by 3. And when you add them, you end up getting exactness. Something that we'll practice later on. Last example, I want to make sure you see how to do this. Solve the matrix for A, B, C. Those are equal. That means what? That means A minus B equal 8. The entries must be equal. B plus A or A plus B must be a 1. Now, can't I use those to solve for, if I add those, isn't that 2A equal 9, which means A is 9 halves? And if A is 9 halves, doesn't that mean that 9 halves plus B equal 1? So B is 1 minus 9 halves, which is negative 7 halves. And if I go for the third entry, it says C plus 3D equal a 7, and negative C plus 2D equal a 6. If I add those, that's 5D equal 13. So D equals 13/5. And once you get that, take any of the equations, say the first, and you'll say C plus 3 times 13/5, that's 39/5 equals 7. So 5C plus 39 equals 35. Subtract from both sides, that's a negative 4. C is negative 4/5. Again, practice, nothing more. That's pretty much it for this section.